Welcome to a lesson with Dr. Powell. Uh, In this video, we're going to talk about the idea of topology and a discrete topology. So first of all, what is a topology? A topology on a set. So let's have a set, for an example, like 1, 2, 3, 4, 5, 6, say. Okay, a topology on this set A is a collection of subsets of A that are in the power set of A. So the topology itself is a collection of subsets. Now, which subsets do we pick? Well, we can pick any of them as long as certain criteria are satisfied. The ones that we choose when we take finite intersections of them. So really topologies work for infinite sets as well. But if we take finite intersections, so intersections of finitely many of them together, those are also going to be in the set, the collection T, and also unions. However, you can have infinite unions, that's fine. But finite intersections and any kind of union is great. So, but in this particular case, I mean, we can pick, like, what if we picked 1, 2, 3, 4, and let's also pick 3, 4, 5, 6. Okay. Now notice that these two sets have an intersection at 3, 4. So 3, 4 itself is also in the collection, and also any union of let's see, and in the intersections here. So we've really counted all the intersections so far. We also need the unions of them. Unions, yeah, since that's a subset, it works just fine. Let's see, as well. So we have intersections, we have unions. We also need, in the topology itself, you also need to always include the empty set and the full set itself. 1, 2, 3, 4, 5, 6. So this would be labeled as a topology of this set A. So it contains all finite intersections of all these guys. It also contains all unions of any kind. So that's a topology. So now oftentimes we call the elements of the topology open sets. So if we're looking in the real numbers, for instance, open sets are open sets are those such that like open intervals are considered open sets. Like an open interval, all the numbers strictly between 1 and 2, that's an open set. Unions of open sets, intersections of open sets, that works. So you get this full topology on R. And you can even say the simple open intervals are actually what you'd call, because you can take intersections and unions of them, and you get the full topology on R, which all of those guys are called open sets. The open interval system, just the open intervals themselves, is called like a basis for the topology, but we really don't need to get into that right now. So pretty much you could think of them as being like open intervals or something like that. Okay, so that is what a topology is. So when we think in discrete mathematics, we study structures where that have the discrete topology. That's where discrete comes from. We don't really discuss that too much, but to be technical, that's what it is, discrete topology. So it's a type of topology, meaning it's a type of collection that where we choose things where we have a certain property holding. Namely, and if we look at the real numbers for an example of something that's not discrete, so we have kind of a notion of closeness in the real numbers. So if we have, like, for instance, let's get a set that looks something like this: a half, a fourth, an eighth, and it goes on forever. Okay, so this is a sequence. Now, let's look at the number 0. 0 is not in the sequence. However, if we take any open set that contains 0, now every open set that contains 0 is going to contain an open interval that contains 0, actually. And any open interval that contains 0 is actually going to have to eke out and also contain one of the elements in this set. That means that 0 is a limit point for this particular sequence. In fact, it is the limit of that sequence, but we call it a limit point because this is a sequence, but really we can do limit points for just an arbitrary set which has lots of sequences in it. And you can have lots of limit points. For something to have the discrete topology, that means that that the only limit points that ever happen are contained in sets themselves. You never have a limit point that's outside of a set. That's what discrete means. It kind of plays off this idea that you don't want things to be too close together ever. Okay, so so let's look at this particular example that that we've come up with, and let's suppose, all right, and let's determine if this is discrete or not. Okay, let's see. Okay, so let's do this. Let's look at the set 1. Let's look at this. Let's look at the let's look at the point 2, for instance. Okay, let's see. Every open set, so anything in the topology that contains 2, so let's circle them. This contains 2 and that contains 2. All right, so those are all the open sets. Now, all the open sets that contain 2 actually also non-trivially intersect with the set, which doesn't have to be in the topology, just any subset of A. It non-trivially intersects with, let's see, 1, 3 even. Just choose 1, 3. What that means is that 2 is actually a limit point of this particular set 1, 3. And in this particular case, there could be more than one limit point for different sets. So because it's kind of a funny finite example. However, but just using these definitions and terminology, we see that T does not have the discrete topology, just like R does not. In fact, in order to get a discrete topology on a finite set, you really have to have everything being its own distinct element. So the topology would have to look like this. So the open sets themselves would have to look like this. The topology would look like this in order for this to really happen. If you have overlaps, you have some problems that arise. I hope this kind of helped you see a little bit about the definition of what a discrete topology is. We look at structures or sets that have this discrete topology. Basically, we just kind of eliminate any notion of closeness and we throw that out. So we're not doing a whole bunch of calculus jazz on things with the discrete topology. Thanks for watching.